Soup too spicy.
Hello. Our group project was a Scuttle mini golf project with Shane Gorski, Ryan McCullough, Daniel Mulder, and Jackson Kingsley. Our initial goals for the project was to have the Scuttle navigate a mini golf course with objects between the ball and the goals. We would differentiate the balls and goal pairs with a preset defined color pairing, and then have the Scuttle shoot predefined colored balls into the corresponding goal, um, avoiding the different goals or colored balls along the way. We would use a trapping mechanism like a cage on the very front of the Scuttle chassis to cage the ball and then hit it with a putting mechanism.
So some challenges we faced. So first, trapping the ball on the front of the scuttle and having a separate mechanism to putt. It was just overly complicated and just didn't really make sense. So we decided to keep the ball between the wheels at the center of rotation, so we could rotate around the ball, kind of orbit around it, and keep it in place while we aim it at a goal. Also, the obstacle navigation during the ball shooting phase wasn't really viable with our delivery system. So we had the obstacle navigation prior to reaching the area with the ball, and we also had a dynamic avoidance. So when an object crossed the robot path, it would stop. And then finally, the shooting mechanism that we had was wearing out really fast. The parts, like the rack and pinion. So we frequently had to swap out the worn parts for new parts while we were testing.
For the hardware design, the design was simple, utilizing only two moving parts of a rack and pinion, and the rack in this system was attached to the hitting portion of the ball. And how it would actuate and shoot would be a rubber band was attached to two posts in the rack itself. So whenever the servo rotated, it would place the entire design under tension. And on the servo pinion on the gear, there's a blank spot where whenever the servo would rotate to that degree, it would releasing the rubber band and hitting the ball. Also, a mounting bracket was used in order to facilitate the rotation around the ball as an orbit because it makes it a lot easier to line up the ball in this continuous movement around it. And yes, this simplicity of this design was the main draw in its use.
So, for software design, as Shane already touched on, we knew that we needed accuracy. Golf is a game about accuracy, and just judging off of the PID lab, we knew that a naive implementation or a naive velocity controller was probably not going to give us the accuracy we needed. And so, for our low-level control, we wrote our own hardware abstraction layer and our own very tight PID loops for the low-level velocity control. And to tune this, we also added UDP-based telemetry based on the LiDAR lab, and wrapped all of this code in a thread model, also very similar to the LiDAR code, or kind of a more like RTOS or synchronous style of I/O handling. Basically, handling sensor data as soon as we got it. Um, our higher level controllers, the different goals we had, avoiding obstacles, aiming towards a ball, shooting the ball, just feed into these low level controllers. And having a really good tune and, as you can see in the graph, pretty accurate and quick responses was extremely important later on, especially like if the battery was low or we were testing on different surfaces, we had some center of gravity problems, and dealing with wheel slippage was a lot easier having a robust lower level control loop. That lower level controller, the motor velocity control, was driven through multiple different higher level controllers, all switched between in the state machine that we'll talk about later. The main ones were when we're hunting for the ball, we're trying to find the ball and get it within a like 1 inch by 1 inch square in the robot without nudging it. That took a while to get there, but we just take feedback from the camera in terms of the heading angle. Once we're aiming at it, navigate towards it. If we veer a little bit or we're swerving, which we did a lot of, we feed in the theta error and the theta PID into the same one. So we kind of switch between the two. The aiming slash putting is the basically the same as the ball hunting, but we only care about theta. We don't care about position. And the LiDAR controller was just keeping track of how close an obstacle is. Are we going to run into it? And where is it? All of these controllers feed into a kinematic model of a differential drive robot, which then spits out desired wheel velocities that the aforementioned low level velocity controller handles. And then that goes to, robot do the thing.
So for our project outcome, so our robot could use LiDAR and navigate static and dynamic obstacles like a wall or a maze, and someone walking in front of it, moving, it'll stop, not hit them. Our robot could also track and carefully approach the correct color balls in the correct color order. And they could turn and aim the correct colored ball around its center of rotation, and it could shoot it into the correct color hole. And then our robot could putt the ball at least 2 feet accurately into the correct hole.
And here is the demo video showing both the putting and the LiDAR sensing.
This first demo was one of our first successful in lab go to ball putt, go to different colored ball, putt into different colored hole. And of note is that the robot can differentiate between all four of these colors without getting confused. And we dynamically switch between what color we are feeding our CV algorithm to get, an accurate position. Um, Notably in this video, you can notice when the robot can, when it sees the ball, it kind of locks on, or here, like it locks onto the target. That's again switching between different control styles, waiting until we see the camera, and once we see it on the camera, locking onto it. This was a later demonstration of the LiDAR obstacle avoidance slash navigating the putt-putt course. By this point in our testing, we had worn through the parts in the shooter. The shooter just wasn't performing anymore at this part of the day. And we do get to the balls after this obstacle avoidance, but I wanted to include us successfully putting and successfully navigating obstacles. With further time, we should have been able to do both in one video pretty easily. Here you can see Ryan steps in front of it, it stops, then it goes back to hunting for the ball. Yeah. Again, you can see it kind of locking on. The controller's adjusting for wheel slippage. And just the level of accuracy that we had to tune it to is very evident here. The shooter was stuck out, which that little difference of maybe a centimeter, the controller was not happy with, so we had to kind of reset the shooter a little bit. Again, it was not performing reliably by this point in the lab. That's why we included the previous video.
So for the technical distribution, we had Daniel. He wrote the main state machine framework for everything to come together, as well as meticulously creating the dynamic closed loop PID for the motors encoders, making a much more accurate PID response feedback loop than we had in lab, to allow for our very, very careful ball approach and the rotation around the ball, which had to be very, very delicate, as well as obstacle avoidance. The encoders were PID was used for. And then he helped integrate our LiDAR camera code that me and Shane came up with. Shane was in charge of creating the LiDAR object class and the threading behavior for the LiDAR, and integrating the LiDAR obstacle avoidance into the state machine. I was in charge of the camera HSV computer vision, creating the object class and the threading mechanisms within the object class, as well as integrating the computer vision code into the state machine and fine-tuning the HSV filters for each of the color objects. To note, both the LiDAR and the HSV computer vision ran on threading behavior, so each ran on their own separate thread, so they wouldn't interrupt the main state machine. Jackson, he CAD'd and designed the ball shooting mechanism and he 3D printed it on his 3D printer, and he ran through several test iterations testing it to make sure that it could work. Um, he designed the mounts for the hardware so we could actually mount the shooting mechanism onto the chassis reliably, and he wrote the servo code for the putting mechanism and integrated that servo code for feedback into the state machine with the continuous servo.